video, what I'm going to be showing is a question that was posed to me on the Attenuator 20:1 video. And the question was, what happens if you reverse the leads? So for example, here I have a 100 volt DC source, and let's say that on the positive output of the DC source you put the negative lead, and on the negative output of the DC source you put the positive lead. So if you were to have the Hantek lead, it would be something like this. Instead of putting the positive to the positive and the negative to the negative, you switch them. So what would happen? So just to explain the diagram here really quickly, these are the leads. So this would be, this right here would be the leads, this area here up to here. And then this here represents the attenuator input. So if you have the attenuator here, these two would represent this part here, and the attenuator output would represent here, and the scope input would be, well, in this case we're using channel 1, would be here. Now if you watch my Attenuator 20:1 detailed analysis video, this would all make sense, and I suggest going to watch that. You can just click here and it'll take you right to that video. Anyway, so here we have the resistor network. The black resistors are the actual resistors that are inside the attenuator, and the green one is the imaginary resistance that happens when you combine R2 and R3. And just to make the calculations easier, I suggest first combining R2 and R3 to get the imaginary resistance of R4. So what happens here if you actually do reverse the leads, meaning you put the positive input to the negative output of your voltage source and the negative input to the positive output of your voltage source? Well, let's look at how many different voltages we'll have here in this resistor network. If we look here, if this is 100 volts here, that means that this whole lead will be at 100 volts. That means everything here that's touching up to these resistors, everything here will be at 100 volts. If we look at this lead, this will all be at 0 volts up to this resistor here. So what will be the voltage here? Well, if you watch my other video, the voltage here should be 95. And that's exactly what it is. It's 95, oh, write that a little thicker. This should be 95 volts. Now you might be thinking, how is this an attenuator? How does this divide the voltage by 20? If it's giving me 95 volts here, isn't that what the scope should be reading? Well, it is. It is reading 95 volts, but you have to think about what is it comparing to. If it's 95 volts here, it'll be comparing it to this side. And since this is the positive input, this will be the quote-unquote higher number. So if it's 95 volts here, what is the voltage here? Well, we already saw, since this is directly connected to the positive output of our 100 volt DC source, this should be at 100 volts. Do you see now? We started with a 100 volt DC source, and through this resistor network we got the voltage down to 95 here, and it stays at 100 here. So if you wanted to know what the voltage across this resistor is, it would be 95 minus 100, which equals -5. And in fact, if you were to connect your Hantek with the attenuator, and you tell the scope that you're using the 20:1 attenuator, and you were to connect to a 100 volt DC source in this manner, you would have 95 volts on this side, 100 volts on this side, and the scope will interpret it as 95 minus 100, which equals -5. Now, in reality, it doesn't actually have to do this math, because all that it needs to know is that the voltage potential between the 2 points is 5 volts, and the current is going in that direction. That's what's really going on. But if you just want to imagine it, this is a great way of theoretically imagining of how the scope is reading. So thanks for watching. I hope I answered anybody's questions, and hope to see you guys again soon.